So in the last lectures, we studied that there are different types of instructions. The instruction can be categorized as arithmetic instruction, logical instruction, or branch instruction. Arithmetic instruction include add instruction, subtract, multiply, divide instruction. Okay, and then logical instruction and exclusive or exclusive not. These provide bitwise. And then we also have shift instruction, logical shift left, logical shift right, arithmetic shift left, arithmetic shift right, rotate left and rotate right. And then we also studied different type of branch instructions. Branch instruction changes the flow of the program. Typically in the microprocessor, the instructions are executed in a particular sequence, and when we want to change the flow of the program, okay, so the branch instructions are used. In the branch instruction, there are also two categories. One was the unconditional branch instruction and the conditional branch instruction. In an unconditional branch instruction, the branch is taken unconditionally. The flow is transformed. An example of this in C or C++ is go to statement. Okay, and then there is also conditional branch instruction. It is actually check the status of the status register. It checks different flags of the status register. The type of the flags that we studied in the status register was N, Z, C, and V. N stands for negative, Z stands for 0, C stands for carry, and V stands for overflow. And and actually, when you check these test flags, there is a preceding instruction. This preceding instruction can be a compare instruction. It can be any instruction. So actually, let's assume if you say compare Q and P and D equal label. So we are testing the flag. So what this instruction, compare instruction, that is preceding this instruction, is changing the flags. Changing the flag. It will change the flag. Which flag will be changed? Which flags? N, Z, C, and G. And this will test the. So this is the example of a condition branch instruction. Okay. Now. So this is a brief overview of the topics that were covered in the previous lectures. Okay, so if we want to initialize some arrays in memory, okay, so we can initialize different arrays in memory at a starting and sub-starting address. If we define any array, let's assume if we have an array of 100, how many memory locations will be allocated? 100 locations will be allocated in memory. Okay, what will be the size of each element? Depending on the architecture that you are using. If the architecture says that integer takes 4 bytes, then 4 bytes will be reserved for each data item. If the architecture says that okay, the integer is of 2 bytes, so actually 2 bytes will be reserved. And maybe some architecture may also reserve, like if we say there is also different keywords in C or C++, long, maybe it takes 8 bytes. So if you want a bigger range of the data, so you can increase the size. Okay, now there is so if you look at this statement in C, so actually, what is array? Array is actually the address of the first element of the array. If you did some pointers, okay. So what is an array 0? If you write this in C, what is this? An array 0. Address of the first element. And array 99. Address of the last element of the array. And now if we say this, what is array? Array is actually the address of the first element. The address of the first element of the array. Now, if we want to have an assembly equivalent of this, if we want an assembly equivalent, so now this is an array, and 100 memory location will be allocated, starting at some address. And typically, the elements of the array are stored contiguously. So now let's assume if we say that now there is a memory location. This is a memory location, and this first element, like if we say, so this is the first element, array 0, the first element, this is the second element, this is the third element, and so forth, so on, and this is the last element. So there are 100 elements. Okay, so now the first element will have an address A, any address and any arbitrary address. It can have any arbitrary address A. Now this arbitrary address. Now what should be the address of the next element? A plus
size of this
size of element. What will be the address of the next element? A plus 2s and A plus 3s and so forth, so on. And it will be A plus 99 S. And if you say that now there is an ith element of the array, the ith element of the array, so the ith element of the array, it means the A plus is. Actually, if you say that ith element, I minus 1, but if it is the ith element but it has an index of I minus 1, it is the index of I minus 1, but it is actually the ith element. This is the first element, this is the second element, this is the ith element. So if we say the address of the ith element is A plus I minus 1 S, there are two things. One is the element number, one is the index. So actually index always start from 0. So that's the reason some people are confused. And why the index starts from 0? Actually the reason is that because it will reduce the number of bits. If you start indexes from 1 and you want to store 8 elements, how many address bits will be used? 4. But to use least number of address bits, so you start from 0 to 7. When you start from 0 to and end at 7, and it is of the power of 2, so you require less number of address bits. If you start the index at 1, so then you may need more address bits. So that's the reason that always the array index is started at position 0 because of the address mechanism. Now, if we want to initialize some arrays in memory, so okay, so what we need, we want to initialize some arrays in memory using assembly. So we need a starting address. So now there are some mnemonics in assembly, and actually it varies from assembly to assembly. It is my assembly, maybe in other assembly the syntax is different. Maybe in some other assembly the syntax is different. Okay, so if we want to reserve some elements, and now let's say if we want to initialize the elements of the array, so there is an instruction org. Okay, so org $2000. So whenever we say org $2000, it means now our starting address is
2000.
So now in this case, if we say org, the starting address is 200. Okay, now let's assume in our previous architecture we assumed a 16-bit architecture for the sake of simplicity. We assumed a 16-bit word size, if you remember. Okay, so now you have this memory width. It starts from $0000. Maybe this portion is for some other data. Maybe you can store some instruction, you can store some data, and you are now starting at location $2000. Okay. Okay, now org, so it means now we are starting address. We assume that the size of this data is 16 bits. If it is 16 bits, it is now 2 bytes. So now if it is $200, what will be the address of the next element? $200? 2. Then $200? 4. $200? 6. And $2008, $2008, $200C, $200E, $2010, and so forth, so on. Okay, so it will go like this. Now, if we want to store some data elements, so now we are using some mnemonics DB. DB stands for defined byte. So it means it defined byte. So 0, 9, 12, $A, B, $3, 6. Okay, this dollars for hexadecimal, not for address. For hexadecimal, whenever there is a symbol dollar, it means now it is a hexadecimal. This is by default is decimal. Decimal. By default, if you are not representing any dollar sign, then it will decimal. Okay. Now, if you write 9, so it means now we are defining byte. How many bytes we are reserving? 4 bytes. Byte 1, byte 2, byte 3, and byte 4. And now if we say we can call it table 1. So table 1, what is table 1? Table 1 is a label. And what is a label? Label is an address. Table 1 is a label. Label is an address. And actually it is the address of the first element of the array. And what is the first element of the array? 9. Okay, so now we start with this. Or now we have two addresses. One is even address and one is odd address. Okay, now we look at this. We are defining a byte. So we are defining a byte. So we are storing the first part here, the second byte here. How will it be stored? 0, 9. 0, 9 and then 12. A, B, C, 0, C. Now if we are writing these values in hexadecimal. So 0, 9 and 0, C. Now what will be the next element? A, B and 3, 6. Now actually what is this table 1? This table 1 is actually a label. You can give any name to it. You can give table 1, array after, you can give any arbitrary, just like if you are defining any variable in C, you say A, B, C. So this is a keyword and this is an identifier. Okay, so this is a keyword. DB is actually a keyword. And this is what? Identifier. Now you see, integer is a keyword, A is an identifier. Float is a keyword, B is an identifier. So if you may give any arbitrary name to any identifier, you may give any name. You may also write your name here. Okay. So table 1 is a identifier, and actually if you don't write this name, it's optional. It's not necessary to write it. It's optional. Actually, it is the address of the first element. Okay, so now this table 1 is actually pointing to this location. Now if you write table 2, we are now defining another table. Table 2. And now we say DW. DW stands for define word. Define word. And we assume that our word is now 2 bytes. Our word size is now 2 bytes. So if we say DW9 and we write it like this, 5, 6, $. So actually this is how many bytes? 2 bytes, 16 bits. Okay. And 3. So 5, 6, 8. How many bytes will be stored?
2 bytes.
2 bytes. So actually it will be equal to 0, 5, 6, 8. It is the address of the first element. And then what will be stored then? 0, 0, 0, 3. So actually if you look at here, so now this table 2 is a label which is pointing to the first element of the second table. So now it is pointing to. Why this address is 2002? Actually the addresses are calculated then in sequence. The addresses are calculated in sequence. Understood? Okay. Now if we say, okay, now this GB, if we have an equivalent in C, what is equivalent in C for this DB. Which data type? Character data type. Character? Actually, it's a character data type. How many characters we have defined? 4 characters. We have defined 4 characters. And now we not only have defined 4 characters, but we have also initialized 8 characters. So we have defined 4 characters and we have initialized these 4 characters. Maybe you write it in string format. Maybe you can say that, yeah, or you can have in this. Okay. Now this table to define word, and now we have then another table 3. Now we have another table 3, and we use this DL. DL stands for long word. DL stands for long word, and long words in our assume we said now long word consists of 4 bytes. And if you want to initialize this thing, so we can say 5, 6, 9, 2, 8. So actually it's a 32-bit data. It's a 32-bit data. So how we can initialize it? So actually it will look like this: 0, 0, 0, 5. The most significant word, and then 6, 9, 2, 8. And what table 3 will be pointing? Where table 3 will be pointing?
2, 0, 0, 8.
Okay. Now, and simple. If we have this 4, how it will be stored?
0 0 0 4.
0 0 0 0 0 0 0. So in this way, okay. So there are some example of different here in notes. So you may go through that. Okay. Now this representation, actually, if we write it like this is in decimals. You can also write it like this: %1,001. This is the binary representation. Okay. This one is the binary. So you want to store it in binary, so you can also represent this in binary. So actually 12. What is 12? 8 plus 4. So it is %1010. Okay. 1, 2, 4, 8. 8 plus 4? 12. So this is the binary representation. If you want to have an hexadecimal representation, so how you can do this? $what? C. $C. So these are different representation, and you may use different representation depending upon your convenience. Okay. So now we have this. This is actually now this is actually the assembly mnemonics, and it is a memory map. This is the assembly mnemonics, and now it is a memory map. And when we have an assembly mnemonics and a memory map, so actually this memory map has some addresses, and now there are some contents. Some addresses and some contents. So this is only this is one view of the memory. One view of the memory when we are storing the data in the memory. When we are storing data in the memory, we are not storing instruction now at this point. Okay. Now, if you remember, we already studied this instruction set encoding, and actually we say that okay now. So, okay. Now we assume another scenario. Okay, so now if we say if we say that now memory can store some data, and memory can also be used to store some instructions. It can be stored, and it can also be used to store some stacks. Stack is also some data, and then you have a pointer there. Okay, so now we assume another architecture. And we assume that now our size of instruction is 4 byte. Our size of instruction is, so we have an instruction and instruction size is 4 bytes. And we studied in our previous lecture that how we have some output field of the instruction. There are some field data reserved for RD, RS1 and RS2 if there is in R type instruction. And if it is J type instruction, so we have an opcode field of the instruction, then we have an offset. Okay, and actually that previous the example that we did in the last class was a very small example, but typically the instruction size is bigger. So the instruction size is bigger, so we say if the size of the instruction is 4 bytes, so how will the statuses look like? So it will 200. 200. Next, what will be next address? 4, 8, C. 2010, 14, 2018, 20, 1C and 20. Okay. So we also use this instructions. So if we say org. Okay, now our assumptions are changed. When our assumptions are changed, the memory map is also changed. Our assumptions are listed. Now the size of each instruction is 4 bytes. So what is here? What is W here? If you remember memory is used as 2A cross W. If you remember, what is W here?
32.
W is 32. Because it's 32 bits. Just link it with that memory. Okay. Now if we say that org $2000, okay, org $2000. So this is our starting point of our program. And now we have some instructions. Instruction I1, instruction I2, instruction I3, instruction I4. Okay? They can be any instructions. Okay? And then we say that jump now look at here I1 is stored in memory in a binary format. I1 is stored in memory in a binary format. So I1 is stored here. I2 is stored here. I3 is stored here. I4 is stored here. And jump label. Jump label is also instruction, so we call it an instruction I5. So where I5 is stored? I5 is stored here. Agreed? Okay. Now I5 is stored. If you look at the jump instruction format, so there are two formats. One was the opcode field, if you remember, and the second field was what? Offset field. And maybe this label, is defined somewhere down here. Maybe label is defined here. What is label now?
Address आपके.
Label is an address. Label is an address. Okay. Now if we say add of I1. I also define a label add I1. What is add I1?
Address.
Add I1 is also a label. Add I1 is
Also
a label. And add I1 is a label which is an address. And it is the address of which instruction? I1. Now if we say, and what is actually add I1? So if we say add I1, so actually what is this address? Now if we say, now this is our instruction and we give a label add I4. Add I4 means address of instruction I4. So actually what is the address of instruction I4? To which instruction it is pointing to memory?
200C.
It is pointing to this instruction. Okay? It is pointing to this instruction, and if we say what is add I4 is actually dollar what?
200C.
00C. Now, if we say, now we will not call it. We can call it add IK. Add IK. What is add IK, a label. And this is an instruction of which instruction? IQ. This instruction will be stored somewhere in memory. So maybe this instruction is stored as some memory. So we have an instruction IK. And let's assume this is IK instruction is stored in memory. And how it will be calculated? It will be calculated by what is our assumption?
The offset rate.
So if we have some intermediate instruction, so actually these instructions are stored contiguously. These instructions are stored continuously. And based on this ORG, all the new addresses are calculated. And in this example, we assume that the size of the instruction is fixed. There are two types of architecture, RISC architecture and sys architecture. In the RISC architecture, the size of the instruction is fixed. In the sys architecture, the instruction size is variable. But in this architecture, we assume that now the instruction size is fixed. So in this architecture, we have an add IK and let's assume add IK. Let's assume that this IK has an address $, 300C. 300C. So what is the address? Add IK. Add IK is pointing to which instruction? So it is $300C. Now if we say, when we encounter this instruction, jump label, it is a conditional jump instruction or unconditional jump instruction? Unconditional jump instruction. So actually it will calculate, okay, now this jump label by itself is an instruction which has an address. We may call it add I5. And add I5 is actually pointing to which instruction? And now, when this program is first instruction, I1 is executed, then I2, then I3, then I4, then I5. Where the control is transferred? IK. Directly, it's just like go to. Just like go to. So now you are jump to this instruction? IK. When you jump to this instruction, so how the processor will this? So actually, processor has one built-in register that is called as a program counter. So the program counter first point to this instruction. It fetches this instruction, it decodes the instruction, it fetches the operand, then it executes the instruction, stores the operand, and then it moves to the next instruction. 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 When it encounters a jump instruction, which is an unconditional instruction, unconditional branch instruction, the control is directly transferred from here to here. And let's assume that all of these I1, I2, I3, and I4 are sequential instructions. They are not branch instructions. So what will be the flow of the program? First I1 will be executed, then I2, then I3, then I4, then I5, then IK. So when the control will be transferred, so now program counter is pointing to this location. When the program counter is pointing to this location, how the offset is calculated? So offset is calculated as address of IK minus address of I5, and that will be stored in this field offset. And this opcode, in this opcode, maybe this opcode is for jump instruction. There is some opcode for jump. Maybe there is some opcode. So when the jump instruction is encountered, when the program counter is at this point, so now program counter is pointing this. So if you want to jump in this instruction, so what we can add? We can add program counter is equal to program counter plus offset, and then automatically jump to the main instruction. And typically, when let's assume the program counter is this, program counter is pointing to this. If you want to jump to I2, how we can do this? Program counter plus
Size of instruction.
Then program counter plus size of instruction. If it's a sequential instruction, so the program counter will be updated. The new program counter value will be updated by the old program counter values plus the size of the instruction if it is a sequential instruction. But when it's a jump instruction, so the program counter value will be added with the offset field. Who will calculate this offset field? Who will calculate this offset field? No.
OS.
Assembler. Now, who does the job of allocating variable in memory in high level language? Who does this job for you? In high level language like C.
OS.
Compiler. Compiler allocates some variables in memory. It's a compiler who is allocating the variables in memory in case of a high level language. But if we see that in an assembly language there is an assembler and an assembly language, and that assembler transforms the assembly mnemonics into the machine level languages. Machine level code, binary code. And we studied this in instruction set encoding. I'm not going to repeat that topic again. Okay, we have studied it how there is an RD field, there is RS1 field, there is RS2 field. It also depends upon the size of the instruction, and in the previous example we assume a very small example. Okay, so now this is how the programs are written.
So नमाज का break ले लें.
Okay, quickly.